So the camera is recording, but because I don't have another tripod, it has to sit on top of the box for the webcam, which means it's too close, so you're not going to be able to see all the board. Because yeah, so I will try to get somebody to set up Teams in such a way that I can record only what I'm saying. Fine. But today we're going to sort of finish off a bit more of NP completeness. I hope I'm going to get through most of it. So if you don't recall, then you can just go back and watch the video for lecture 13. If you recall, in lecture 13, we were discussing so clique and independent set and vertex cover, and we said, yeah, okay, obviously, if you can, this is almost like if you come up with a polynomial time solution for any of them, then because you can convert each of them into the others in polynomial time, you get a polynomial time solution for all of them. So this is sort of like saying, if you can find, when we found a linear time algorithm for max sum subarray, we automatically got a linear time algorithm for max sum subarray in a circular array, right? That was why we were doing that, to sort of teach you that people actually do this kind of thing, this code reuse, this idea that if you have an algorithm for one problem, you can use it to solve other problems. Usually you use them to solve similar problems, but sometimes you can make problems turn into other problems in sneaky ways. Okay, so clique independent set vertex cover, that was pretty easy. And then we said, okay, there's, we could do clique into sat. That was not so easy, because it was easy to say that if you have this vertex in the clique and this vertex in the clique, then there better be an edge between them, because we just had for each pair of edges, for vertices which don't have edges between them, they're not both in the clique, right? So we just had a variable for each vertex saying whether or not it was in the clique, and then for each missing edge, we just said not XA and XD. Okay, so we saw that we could use SAT as sort of a language to express other problems. We could take what looks like, what is a graph problem, clique, and we can write a formula that says this graph has a clique of size k. The tricky part was saying of size at least k. The tricky part, well, or exactly k, because if it has at least size k, then it has one of size k. The tricky part was saying this k stuff, because there, if we just go through and say so one of these subsets of vertices of size k is in there, that took too long, so we had to do that dynamic programming style table, which, don't worry, I wrote it up and sent it to the scribes, so there'll be a nice version in the scribe notes. And then we did this Satan transformation, which showed that you can reduce. So from SAT, given a Boolean formula, you can sort of write it as a circuit, and then for each gate, you can sort of, you assign a variable to the output wire, and you write a little formula that says the output is true if and only if it should be. Right, so and then we took this, so that way we could turn SAT into 3SAT. So we had this thing where clique could be the sat could be turned into 3SAT, all in polynomial time. So therefore, clique reduces to sat in 3SAT in polynomial time, and then we finished with the proof that 3SAT can be turned into clique in polynomial, given an instance of in polynomial time. Given an instance of 3SAT, we can generate in polynomial time an instance of clique, a graph G and an integer k, such that G has a clique of size k if and only if our input formula is satisfiable. Right? So we start to see that all these problems, so given an instance of vertex cover, we can turn it into an instance of 3SAT. Given an instance of a 3SAT, we can turn it into an instance of independent set. So now we're going to see that this spreads a little bit wider. Okay, so we're going to go right back to the beginning of the course, and we're not going to talk about Eulerian cycles, although we could. That's not a hard problem. Remember, we saw a polynomial time solution for that, but it does reduce to SAT. If you want, you can think about that after class. What I'm going to show you is that HEMPath reduces to SAT. Okay? So what we had was clique, independent set, vertex cover, and then we had SAT, and obviously 3SAT reduces to SAT, but what we showed was that actually SAT reduces to 3SAT, and then we showed that 3SAT reduces to clique. All of these arrows mean that there's a polynomial time transformation, polynomial time reduction. Okay, so now we want to say, how does HEMPath fit in here? So suppose we're given a graph G. This is very crowded. So if I'm using other software, it can be further back because it, I don't know why, but it zooms the screen. And then you can actually see the whole screen using the PowerShot. So the camera is running, yeah. Camera is running, the is running. So think about this, you're given a graph G. Now we saw on Monday that given a graph G and an integer K, you can write this formula for clique. So what about, let's just say there's a Hamiltonian path, and we don't even particularly care where it begins and ends, for example. So this is a bit of a weird Hamiltonian path. Usually you get the starting point and ending point. So what is, how can we write this using Boolean logic, using propositional logic? Well, for each, let's have some graph. Like this, okay? So can you see this? Maybe? Kind of. Yeah, okay. So I'm going to try it with black. But the black mark, I should have got new markers. Among all the other stuff, except I was messing around playing with Teams and Google Meet and Zoom. Is that better? Okay. So let's say there's A, B, C, D, E, F, G. So what we want to do, now I just made this graph up, so I don't know, I think there is, yeah, there's a Hamiltonian cycle, right? Because you can just go A, B, G, F, C, D, E. Okay? It's not cycle, path. I don't know if there's a, yeah, I think there's also a cycle because you go B, A, F, G, E, D, no, I don't know. Okay, but it doesn't really matter. Okay, so what we're going to do, we're going to create a variable that's x I, v. Can you read this? No. Maybe the writing is better in blue. So xiv. Okay. Okay, so I have diagrams in black, writing in blue, or maybe you can see it when I write in both. So this means that vertex V appears ith in Hamiltonian path. Okay. So we're going to have all these. So obviously, every vertex has to appear somewhere. Every vertex appears only once, and you can't have two different vertices appearing in the same position. Okay, so we're going to have for how many? 1 less than or equal to I. Wait, no, let's. Okay, so for U, V in, so capital V is the vertex set of F. We have not and 1 less than or equal to I less than or equal to N. Not the case that X, I, U and X, I, V. Okay, so we add a clause that says for every I between 1 and N, and for every vertex U, U not equal to V. Okay, so I should say here U not equal to V. Okay, U not equal to V. And U not equal to V. So for every pair of vertices that are different, they don't both occur in the ith position. Okay? And then you have for I, J, well, 1 less than or equal to I, yeah, this is what I was doing, less than J, less than or equal to N, and V in V. So this is probably the small camera can't see this anymore. We have not X, I, V, and X, J, V. Okay? And then, okay, so going over here, we have for V in V, we have either X1V or X2V or X3V or XNV. So this is just saying that for all of the vertices, they appear somewhere in the path, right? So we're saying, I should stand in front of the microphone. We're saying that for any pair of vertices, they don't occur in the same position in the path. For any I and J, no vertex appears twice. Every vertex has to appear. Okay. What else do we have to say? Come on, it's 11:30. It's not that early. What else do we say to guarantee? So in these formulas, to say that this is that if this formula, we take all of these restrictions and we concatenate them, we conjoin them, we put ands between them, and it's going to be equivalent to saying that this formula is going to be satisfiable if and only if this graph has a Hamiltonian path. What else do we have to say? What restrictions do we have to put on? Second condition is no vertex appears twice, right? So if you have xiv, so xiv means that v appears ith in the Hamiltonian path. And xjv, so it says it's not the case that it's xiv and xjv for some j not equal to I. But, so we've got sort of the conditions, nothing appears twice, everything appears, and no two things occupy the same position. What else do we need? That would be a cycle. If we were talking about a Hamilton cycle, which we were talking about at the beginning, yeah, no edge appears twice would be Eulerian cycle. Well, okay, in an Eulerian cycle, you cross every edge once. In a Hamiltonian cycle, yes. I'll just finish. In a Hamiltonian cycle, you can't cross any edge twice, because if you did cross an edge twice, you'd have to visit the same vertex. Yes, so that's what people are saying now. You have to guarantee that if I go from xiv, so from xiu to xi plus 1v, there had better be an edge between u and v, okay? Because I want it to actually be a Hamiltonian path in this graph. So far, we haven't said anything about the actual graph. We've talked about the vertices, but we haven't talked about the edges yet. So we have to say that we go through, and for I 1 less than or equal to I less than n, yeah, and u v in v, if uv is not in, I know you can't read this, but it's not the camera, it's Collaborate Ultra. If uv not in the edge set, then not xiu and xi plus 1v. So we go through and we say, okay, well, it's being recorded in the high definition camera, but because the Collaborate Ultra wants this camera to be so close, this camera has to be too close, so you can't see the whole board. So afterwards, I'm going to go and complain to tech support that it's not my camera, it's their software. So I don't worry about it until Christian worries about it. I worried about it a little bit, but then Christian and Andrew worry about it more, and then they tell me that I should be worrying about it. But okay, we go through and we say that if there isn't this edge, then you better not be going from u to v. Okay, so we write this, all of these things, when I write this for u and v and for I, these you can say, I mean, how many pairs of edges are there? Well, n squared. How many of these? So this is like cubic, this is like cubic. So this whole formula is going to be like cubic size, right? It's going to be like O(n) to the 3. So it's polynomial. So given a graph and well, just given the graph, I can write a formula that basically says that is satisfiable, that says the Hamiltonian path in this graph, and then I can that formula is satisfiable if and only if the graph actually has a Hamiltonian path. So here, I could go through and put an example of each of these things with this graph, and maybe the scribes will do this, saying like, okay, for U and V, so it's not the case that C is the fifth vertex and E is the fifth vertex as well. It is not the case that C is the fifth vertex and C is also the seventh vertex. Are there 7 things? 1, 2, 3, 4, 5, 6, 7, yes. It is not the case that if A is the second vertex, that G is the third vertex, because there isn't an edge. Okay, so you write this. So Ham path, sorry about that. So Ham path okay, I'm just going to move 3sat. I'm going to move the label for 3sat over here. I know this is, so Ham path so in polynomial time, Ham path reduces to sat. So if we had a magic box that could solve sat, we could use it to solve Hamiltonian path. Okay? That's not super surprising. Okay? What's a bit more surprising is what I'm about to do now, which is 3sat reduces to Ham path. Okay, so this is going to be a diagram, so I'm going to use black and maybe blue sometimes for the writing. So the idea is if somebody gives us a formula in 3CNF, we want to be able to build a graph such that that graph has a Ham path if and only if the formula is satisfiable. Okay? So what formula do we want? Let's do something simple. So x1 and not x2 and this isn't or, sorry. Or x3 and not x1 or x2 or x3. So this is, oh, okay, let's, yeah, okay, this is obviously stupid because I could just choose like x3 and satisfy everything. But I'm going to, do we want to do another one? Yeah, sure. And x1 or not x3 or not x4. Now, is that satisfiable? We can do x1 and get those two, and yeah, then we just do x3. Yeah, okay, it's satisfiable, but it's a bit more interesting because we actually have to, I don't think we can hit everything with one variable. Okay, so how are we going to do this reduction? Well, we have, just to make it easier, we're going to put a start vertex here, okay? So we're either going to have to start or end here. And then for each clause, we're going to have a sort of a diamond. Okay, so this is going to be for clause 1. This is going to be for clause 2. And this is going to be for clause 3. And then just to make sure that it has to go from here to here, so it has to begin or end here. It has to begin or end here, right? Because once you're here, you can't go. If you start here, you can't get back. If you end here, you can't leave. So either it starts here and goes to here, or starts here and goes to here. Everybody's happy with that? Okay. So we're going to be resetting. We're going to be starting the little camera again. Reset, start. Okay, so the little camera doesn't see very much, but okay. So how are we going to do this? Well, so let's call this S. So this is actually, wait, this is a diagram, so it's supposed to be in black. I have to get better overhead markers too. That I can do something about. Except Staples didn't have better overhead markers when I was there. Okay, so how are we going to do it? Remember each clause here. So for each clause, no, sorry, I got this backwards. For each variable, yeah, sorry. I got this backwards. For each variable, I have a diamond. So I'm going to have another diamond. I'm going to have another diamond here, which I'm sure the little camera is not going to be able to see. Okay, for each variable, I have a diamond. So I have 4 variables, x1 through x4. So I have 4 diamonds. And then over here, for every clause, I have, I'm going to make this nice and big. So for each clause, I'm going to for each clause, I'm going to have a vertex over here. So this is clause 1. Clause 2. Clause 3. Now, for in the diamonds, what I'm going to put is, so I have to do this just right. What you're going to have is so you have to do this. So I'm going to put, so we go this way on the, so this is x1, this is for x2, this is for x3, this is for x4. If we make x1 true, then we're going to go this way over to, we're going to put a path in here. We're going to go over to here, and then we're going to go like this, right? So if x1 is true, then, okay, so if you make a variable true, you do this. You go like this, and then over to here, and then down. So this is true. And then if you make it false, you want it to go like this. Okay, so so you have to put the path in in such a way. So basically, you're going to put a little chain of vertices in here. And now, maybe it has to be directed hand path. I don't. Just a second. I have to check that my notes again. Yeah. Why did okay. So I'll just so what you want to do is have this so that you can go here, but how do you stop it? How do you stop it going back? Oh, right. I think, okay. Just a second. Okay, I've just forgotten one of the details of how this works. So the idea is going to be you start here, and if you go through, so you're going to connect. If this is if you're going this way, okay, I know how it works for directed. So for the moment, I'm going to say it's directed. So the graph, the edges only have direction. Okay, so you have to start at S, and my marker died at a really inconvenient time. So if it's directed, this is why blackboards are better. Okay, if it's directed, then it's easier. And if it's undirected, then you can still do it, but I forget how. If it's directed, you don't actually need these extra vertices because I can insist that it has to. So obviously, if it's directed, it has to start here, and it has to end here. So it's directed, then what you're going to do is, for each of these vertices in the middle, you're going to allow, so if x1 is true, so you're going to have, say I just put two vertices here. So this, you can go from this vertex, so you can go from this vertex to this vertex, from this vertex to this vertex. You can go also like this. Right. So it's just a chain of vertices that look like, you can go from one to the next or backwards. So it's like a doubly linked list. But the trick is x1 satisfies clause, so actually I'm going to have more of these in here. I'm going to have 3 of them here. But same thing, just paths, so I can go like this. Now, x1 satisfies, if I've set x1 to true, so I'm going this way, then I can go and satisfy clause 1. Okay? So instead of just crossing directly from this side to to this node, I can say, okay, I'm going to jump over and visit clause 1 and jump back. Okay? So x1 does not satisfy clause 2. Not x1 does, but x1, actually maybe I only needed a couple of these things, 2 of these. Okay. But it does satisfy clause 3, so I'm just going to put, I go from x1 to clause 3 and then back. Actually, okay, so I don't need 3 vertices, I only need 2. Now, not x1 satisfies clause 2. So here, so the difference is, if I have the 2 vertices and they're like this, and if x1 satisfies this clause, then I can go and visit the clause vertex on my way from left to right. Right. So if I decide to go down here and go over, then I can visit clause 1. But if I decide to go down, so maybe there's another clause, so this is clause I, and this is clause J, but if maybe the negation of x1 or of this variable satisfies clause J, in which case I connect this like this, such that I can visit clause J on my way from right to left. Okay? So here it would be x1 satisfies clause 1 and clause 3, but not x1 satisfies clause 2. So notice that if I want to go from here to here, and I go down here, and then I can visit clause 1, and I can come back. And then I can go over here. I can't visit clause 2 because the arrows aren't going the right way. And you can make it so that this works even if they're not arrows, they're just edges. So I can't visit clause 2, but I can visit clause 3 and come back. And now I'm here. And now I can go here. And now I can decide whether or not I want to go down to the left and over to the right and down, or if I want to go down to the right and over to the left and down. So for x2, I'm going to set not x2 satisfies clause 1. So it's going to be from here. So I'm not going to draw the arrows because you're not going to be able to read them. From x2, for x2, if I go here, I can't visit clause 1 if I'm going left to right, but I can visit clause 2 and come back, and then I can't visit clause 3, so I go over. Whereas if I go from the right to left, I can go down. I can't visit clause 3, but I can't visit clause 2 because I'm going the wrong way. The arrows to clause 2, I have to go here and then to clause 2 and back. So, but I can visit clause 1 because the arrows will go from here to clause 1 and back. Okay, you can find this online, and presumably you can also find it without the arrows. There is a way to do this for undirected hand path. I've just forgotten that detail right now. So this is how you build a graph. You can see that if there is a way of satisfying, now notice that once I visited clause 1, I can't go back, but that's fine. once I've assigned a truth value to a variable that satisfies clause 1, I don't need to satisfy it twice. These are ORs. So I just need to have either x1 is true, or not x2, or x3. So I just have to hit each clause once. So if there is a truth assignment that satisfies the formula, then there exists a way for me to walk. So in this case, it would be, say, x1 and x2. It would be like here, go over here, here, over here, and over. And now I don't care about the rest of them. I can go either any way I want. So yeah, so I'm going to make, it's basically this. So if there's going to be, for each, there's a chain of vertices. So in the diamond, there's a chain of vertices going from left to right and from right to left, because each of them has, they look like this. So you can go, if you decide to come down to the left first, then you go over to the right, and then you come down. Did somebody say something? Okay, no. There's always, I mean, you only actually have to have as many as for each clause the literal appears in. You want to be able to say it goes over to the clause and comes back if it appears positively, or it goes. You want to have it so that you can hit the clause and come back. So if the variable only appears in one clause, you could actually have it go here, here, or vice versa. You can always make it the number of clauses, yeah, minus possibly. It's safe if you make it the number of clauses. I think you can always make it the number of clauses minus 1. So if you want, we can take the time, because this would be clause 1, clause 2, clause 3. Yeah, in this case, I could do it with 2. Why I had 3 here, that was just me being, trying to think on my feet. So yes, you can always do it with number of clauses minus 1, except if a variable, if a variable doesn't appear in a clause, neither just by itself nor negated, then all it will look like is this. There won't be one of these routes to a clause vertex. So that's how you can take handpath and reduce 3-sat. 3-sat reduces to handpath. Now, okay, this is directed handpath. There is a way to guarantee that, because here there's a way to, maybe I'm remembering the proof to directed handpath, but there is a way to do this such that you can't cheat. But I can't remember the details. Oh, right. Explain how to get, okay. So, yeah, okay, I won't check that right now. I know how to do it. So undirected handpath is, so directed handpath is hard, undirected handpath is also hard. But I'm running out of time. Okay, I still want to get through a bunch of stuff today. So, yes, okay, so we have the link for how this works. So now, I want to go to the other problem we studied right at the beginning of the course, and I'm going to leave this part up here. Oh, that's embarrassing. I can't remember this. So I'm going to do 3 colorability. So how, oh, I shouldn't have erased that graph. But okay, whatever. Imagine you have, yeah, okay, I mean, whatever. You have a graph. A, B, C, D, E. Okay, is this graph three-colorable? Probably yes. I think so. Okay. You want to be able to say, you want to be able to write in, I was focusing so much on the writing stuff as formulas that I forgot to study the standard proof. I studied it and then I did the formulas. I must have forgotten the details. Okay, how would you write a formula that says this graph is three-colorable? Well, you have, for each vertex, you're going to have three variables. So XA blue, XA red, XA green. Okay, so we're going to say first either XA, well, okay, I can reuse this. You're going to have a clause that says either XA blue or XA red or XA green. You're going to have stuff that says it's not the case that XA blue and XA red, and it's not the case that XA blue and XA green, and it's not the case that XA red and XA green. So you just, so etc. So this is saying every vertex has a color. This is saying every vertex has only one color. Okay? And now you want to say, okay, it is not the case that XE red and XA red. And it is not the case that XE blue and XA blue. Okay? Blah, 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 blah. So for each edge, you go through and say, okay, it's not the case that the two endpoints are the same color. Right? So you just have to say, it's not the case that they're both blue, it's not the case that they're both red, it's not the case that they're both green. So this is not that hard, right? I mean, you can see how to write this graph, write the formula that says this graph is three-colorable. So we can reduce, that was a bad place for hand path. Hand path is going to be here. Hand path is here. So hand path reduces to sat, and 3 sat reduces to hand path. Now we have 3 colorability reduces to sat. Okay? Now we're going to do 3 sat reduces to 3 colorability. And we're going to do it with our cute little formula up at the top. We'll understand this, the fact that given a graph, you can write a formula that's satisfiable if and only in polynomial time, you can write a formula that's satisfiable if and only if the graph is 3-colorable. Are people happy with that? Okay. So I mean, this is what I'm saying about, like, I know the proof of I know the ham path proof. Yeah, okay, I need to do this again. But I was fighting with Zoom and Teams, and I was making people call me in Teams because if I check the recording, it looks fine, but then if I check the recording when there's more than one person in there, then it looks bad. And now it's not, okay, now it's nice and exact, but you just can't see very much. So I should have gone over the proof, but okay. The rest of it, I shouldn't try to do things from memory when I realize how long ago I last taught this stuff. I mean, I haven't taught it for at least a year, and I learned it, okay, I learned it 20-something years ago. I've seen it more recently than that, but okay. How are we going to, so we don't need this graph anymore, because now we're going to take this formula and build a graph. In polynomial time, we're going to build a graph such that the graph is three-colorable if and only if the formula is satisfiable. So what we're going to do is, the first thing we're going to have, so this is, we want black for the diagram. So we have a triangle. We start with a triangle. And this is going to be, no, actually, let's make the triangle upside down. Right, so this is, it's going to be like this. So this triangle, you can color, like, let's suppose the colors are red, blue, and green. So I don't care how you color this triangle. Right? I can't control that. But I'm going to say that this is the true vertex. And this is the false vertex. And this vertex is called base. Okay? So whatever color you would color this, that color is going to be true. Whatever color you color this, that's false. And whatever color you color this, that's base. So now, for each variable, I'm going to build another little triangle. So this is going to be x1, and this is going to be not x1. Okay? So I don't know, I don't know if you color this true and this false, or this true and this false. But I know that you have to color exactly one of them true and one of them false, because you can't color them base. They're connected to base, and so the options, and they're connected to each other, so they can't both be true and they can't both be false. So I'm going to have that for each of my variables. x3 not x3, x4 not x4. Okay. Now, what I'm going to do is, okay, I'm not going to draw the lines here because it's just going to be but when I draw a vertex here, it's this vertex. I'm just not going to draw the lines to this vertex. For this clause, what do I want it to be? Well, I'm going to have x1, which is actually this, okay? I'm just not going to draw the lines here. I'm going to draw the vertex again, but it only appears in the graph once, okay? So I'm going to have x1, let me make that bigger and darker, x1. and not x2 and x3. And don't worry if it's not on the high-res thing, it's all over the internet. And I think it's probably in the textbook. And I want to have, okay, you could see me choking to death. Okay, so I want to have a vertex that can be true if and only if this clause is satisfied. Okay? So what I'm going to do, I'm going to buy new markers. I'm going to create, so this sort of works like an and, right? So suppose that this is true, meaning it's the same color as the vertex true. Can you see all the way down here? Yeah, okay. But not in the little camera phone. So this is, if this is true, or this is true, let's suppose that, remember, each of these either has to be true or false. So if one of them is true, then I can color, if this is true, I can color this base, and, sorry, it's not an and, it's an or. So if this is true, so let's actually these red, blue, and green. So let's say true is red, false is blue, and base is green. I'm not sure. I have 20 minutes, so maybe. So let's suppose that x1 is false. So not x1 is true. So x1 is false. But let's suppose that x2 is also false. So not x2 is true. Okay, so if at least one of these is true, then I can color, one of these can be base, right? And one of these, the other one can be false. So I can make this one base, and this one is false. Which means I can make this one true. So if you run through and okay, if one of these is true, then the thing opposite can be either false or base. If the other one is true, if this one is true, then this can be false or base. So these can't both be false, but they can be base and one can be false. So if you run through, if you color both of these true, you can color this one true. If you color one of these true, you can still color this true. If you color both of these false, if this is blue and this is blue, then these can't both be green and they can't be blue. So one has to be red and one has to be green, and that means this has to be blue. It has to be false. So now I do the same thing again with connecting here. So x3, what do? We want x3 to be false, say. Wait, here. I have to do that. I have to move it over a little bit. It has to be like this. Okay. So if this is blue, so this one is red, so I can make this one blue. This one is blue, so I can make this one green. So I can make the whole thing red. Okay? So if at least one of the literals in clause 1, so this is called a gadget. So when you break the reduction up into pieces and you say, okay, for each clause I'm going to have a gadget, or for each variable I'm going to have a gadget, and then you figure out how to build the gadget, and then you can say, okay, and then I do this for all of the clauses. Okay, so so this is a clause gadget, and it's a subgraph that is arranged in such a way that I can color this red if I can color this the same color as this, if and only if I've colored at least one of these the same color as true. So I can make the output is true if and only if the input is, there's a way to color it with 3 colors such that the output is true if and only if one of the inputs is the same color as true. Okay? So I do that for all of the clauses. And then the final thing, so actually remember, this was not x1. So this is actually here. And not x2, this is actually here. And x3, this is actually here. Okay? So now I do that for all of the clauses, and now I take the output vertex for each clause, and I connect it to false, and I connect it to base. So that means I'm saying this has to be the same color as true because it's connected to false and base. So you end up with a graph that you can 3-color if and only if the formula is satisfiable. Okay, so this is a polynomial time reduction from 3-sat to 3-colorability. Are people happy? It's not so easy to do with like low-res transmission software and stuff like that, but this is all over the internet. You can find that. Notice, so we now have this edge. 3-sat reduces to 3-colorability. So now, clique, independent set, vertex, cover, sat, 3-sat, 3-colorability, ham path. If you solve one of them, you solve them all. Notice this also means, I shouldn't have erased. Remember I drew that graph and I said, is this graph 3-colorable? And I wrote a formula. Well, I said how to write a formula such that the formula is satisfiable if and only if the graph is 3-colorable. You can also do that with 4-colorable, right? So you can easily say, okay, I can write out, okay, each vertex has to be one of 4 colors, no vertex can be 2 of the colors at the same time, and vertices at different ends of the same endpoint have to be different colors. So you can write a formula for 4-colorable. So you can say, okay, SAT four colorability is reducible to SAT. 5 colorability is reducible to SAT. And remember, we showed, it's not planar, but we observed at the beginning of the course, it's in the scribe notes, that you can reduce 3 colorability to 4 colorability and 4 colorability to 5 colorability, because if you have a graph G and you put a vertex, a new vertex, and attach it to everything, if G was 3 colorable, then the resulting graph is 4 colorable, and if the resulting graph, if this is 4 colorable, then G is 3 colorable. So 3 colorability reduces to colorability, and 4 colorability reduces to 5 colorability, and so on. But 5 colorability reduces to SAT, and SAT reduces to 3 SAT, and 3 SAT reduces to 3 colorability. So you can also reduce 5 colorability to 3 colorability. So these problems, if you solve 3 colorability, you solve 5 colorability. Okay, we already knew that if you solved 5 colorability, then you could solve 3 colorability from way back when. So the other thing, I mean, this is not, all of these problems are, we don't know how to solve any of these. But I don't want you to think that only hard stuff can be reduced to hard stuff. So for example, I can also do two colorability. Okay, 2 colorability reduces to SAT. 2 colorability reduces to 3 colorability. But not the other way around as far as we know. So if I give you a graph, you can write a formula that says that graph that graph has a 2 coloring. But that would be a silly thing to do, because we know how to solve 2 colorability. You just do sort of a breadth first traversal. So you can reduce an easy problem to a hard problem. You just can't go backwards. Okay, so Eulerian tours, or Eulerian cycles, I can write a formula that says a graph has an Eulerian cycle. But why would I want to? Because I know how to determine if a graph has an Eulerian cycle, but in general, we don't know how to determine if a formula is satisfiable. But you could do it. Nobody's going to stop you. I mean, it's possible to do a reduction for things for which we have polynomial time algorithms. You can still turn them into problems for which we don't have polynomial time algorithms if you want. So this is, so I'm not going to get quite as far as I wanted today, but I got most of the way through this stuff. A lot of this stuff is, well, somebody found this stuff. It is online. What you generally don't find online is this idea of taking a problem and saying, taking a graph and saying, can I write a formula such that the formula is satisfiable if and only if this thing has a hand path? I'm doing that differently than most instructors because I want you to realize that SAT is really powerful. So I'm going to give a hint of the next, I'm going to have to do it in the next class. The hint is, so how do all of these reductions to SAT work? Well, you have this problem and you think, okay, I want to write a formula such that the formula is satisfiable if and only if the instance of this other problem has a solution. And remember I said that this is sort of like a programming language, right? You're using SAT like a little programming language. You're trying to write like a program. That formula is sort of a program such that the formula is satisfiable. Okay. So what do we do with programming languages? SAT is not a really powerful language. It's not that easy sometimes to see how to rewrite a problem as a SAT formula. But with programming languages, if you only have a very big, like if somebody gives you a machine and it doesn't, nobody does this anymore because we all have the internet. But if somebody, before we had all these powerful compilers, what would you do? Well, if you want a high-level language, if you want to program in Python, you really, really want to program in Python, but your computer doesn't have Python. Or in fact, nobody's ever written a Python compiler or interpreter. Then what you could do would be maybe your computer, maybe all you have, there's been a global catastrophe and all that's left is assembly language. You could write a basic C compiler in assembly language. And then you would use the C compiler to write a better C compiler, and then you could use that C compiler and write a Python compiler. Okay? So we build up, if you have to start at the very basics, you just have machine language and you write an assembler and then you write a C compiler and then you build up until you have these very powerful languages. So what we're going to be doing in the next class, which I'll just sort of skim through in the next 6 minutes, is we're going to think, okay, how could I write a more powerful language and sort of compile it down into SAT? Because why would we want to do this? Well, in theory, you can see here that all of these problems, okay, let's take this out, because this one, it still reduces to SAT, but I just want to talk about these ones that you can get from SAT to any of these, and you can get from any of these to SAT. So this whole network is called a strongly connected component. So you can follow the arrows and get from anywhere to anywhere else. When we had two-colorability, you could get from two-colorability to anywhere else, but you couldn't get from anywhere else to two-colorability. Okay. All of these, we can see, we could talk about this network and say, yeah, okay. If you could solve any of these problems, then you could solve in polynomial time, then you could solve in polynomial time all the problems for which you can write a polynomial size formula saying that the problem it has a solution, right? So if I come in with some other problem and you can see how to write a formula that says that it's a yes instance, an instance of this problem is a yes instance. So if you can do that, if you can write the formula saying that the instance is a yes instance, then you're reducing it to SAT. And so if you solved any of these problems, you'd solve SAT, and so you would solve that other problem. So the class at the moment would be, we can see that there's this class of everything for which we can write polynomial sized formulas saying that problems are solvable, saying that the instance of the problem is a yes instance. But that's very clumsy. I mean, it doesn't feel like a natural thing to want to say, right? So instead, what we want to say is, for example, whatever your favorite language is. In the next class, we're going to go over, I want to be able to say, if I can write, say, a C program, such that given a problem, I can write a polynomial size C program that in polynomial time checks a solution, then that class of problems, if you solve any of these, you've solved all these problems. So that's going to be more powerful. It's going to say for any problem for which you can recognize a solution in polynomial time. Basically, write a C program that recognizes a solution in time polynomial the size of the instance. Then if you solve any of these, you solve all those problems. And how are we going to do that? Basically, we're going to take, well, we know that you can, if you have assembly language, you can compile a C program down into assembly language. So if I can write programs in assembly language, if I can write a program in C, I can write it in assembly. So the idea is show that if you can write a program in assembly, so a program that runs in polynomial time, then you can write a logical formula, a propositional formula that says this program runs in polynomial time. This program says yes. So once we've done that, then we're set. Okay. So that's why, because normally people don't bother saying I can write 3 colorability as a formula. They just say it's possible in polynomial time to check, given a 3 coloring of a graph, to check that it's a valid 3 coloring. They don't worry about actually reducing it to SAT, because they just say, okay, well, it's in polynomial time, I could write a program that would check a solution. Because in the next class, we're going to see that you can reduce the problem of, check a solution. We're going to reduce it to SAT. So we're going to have another node over here. This is getting a bit crowded, and it's going to say sort of check us, does a program say yes in polynomial time? It reduces to SAT, and so now anything for which you can check a solution in polynomial time, if you solve any of these, you solve any such program. Okay. So that's Cook's theorem, the famous Cook's theorem, that recognizing a solution in polynomial time reduces to SAT. So also this class, I absolutely need to get new markers. I was looking because the math department apparently has really good overhead markers, not overhead markers, whiteboard markers. And so Sarah says that she can get me some. So I will try to get her to get me some for Monday. And I will try to get somebody to do this Teams live event software stuff. Okay, that's the end of the class, I think. And I will check what I think it's just a small change to make it work, that proof work for undirected, but I couldn't remember the detail. Okay, thank you. Everybody happy? Any questions? Thanks. Have a good rest of the week. Good luck with assignment 3. Okay. Please go to the tutorials. Okay. Okay. There will be more NP completeness reductions in the tutorials. Okay. Thank you. I will stop the recording.